welcome back to more work with floating point numbers. You may have thought you've seen enough floating point numbers last time that's enough for one lifetime. Well, that's true. We won't talk any more about this IEEE standard directly, but we'll look now at the impact it has on real calculations. So this is the second part, and this is important. Not only is it important, it actually has some interest in its own sake. So let's look at the first slide and see what we mean. Look at the first slide. There we go. Okay. Well, one of the things that scientists have done is to say when we deal with computer programs and we deal with finite digits used to store numbers, we have limited precision. And I don't know about you, but there was that table we looked at in the first lecture on floating point numbers, and there was lots of numbers to memorize. The truth is, you don't have to know all those things. I mean, it's good you can impress your computer science professors, but if you want to impress me, what I want you to know is two basic facts, okay? If I'm dealing with single precision numbers, I only have 6 to 7 decimal places in the mantissa and a limited range for the exponent. And if I'm dealing with double precision numbers, then I have maybe 15 to 16 places of precision. Okay? And so we'll talk about this. Those are the things to remember. And on a computer, we model this by saying, for any computer, really any computer language and software implementation, there's a certain machine precision. That's what this slide is about. And it tells you how accurate the computer is in a single number for any calculation. And once you know this number, you can tell your algorithms, this is the best I can do. Don't worry more about that. So let's look at an example to see what this means. Okay? So here in the middle of the slide, we see what happens if I'm doing a single precision calculation and I add the number 7 to another number, 10 to the minus 7th. What do I get as an answer? Well, computers are smart. They're very expensive. They can do all this. Well, yes, but if we go back, and I lied to you. I told you we're never going to show you another one of those IEEE notations, and here we have it again, but don't believe everything you hear. Okay? How is the number 7 stored on the computer? Well, it's stored here in white as this long series of bits with a mantissa. Here's the sign bit, exponent, mantissa. And likewise, the number 10 to the minus 7th is stored, also a positive number, with a mantissa and an exponent. Well, we can't just add these two numbers together. I take it back. We can add those two numbers together, but you get the wrong answer. Okay? If you were doing this on the computer and you wanted to get the right answer, then you have to have the exponents match, because when you're adding two numbers, if the exponents don't match, you just can't add anything. It's wrong mathematics. You can do it, but it's wrong. And if you get the exponents to match, then you can add the mantissas. So the way you do this on a computer, how do you make the mantissas the same? Well, you just keep shifting over. You put in more zeros and then change the exponent each time, like you do in any scientific notation, till the mantissas are the same. So if we look here at the yellow version of 10 to the minus 7th, we see, aha, we can also write 10 to the minus 7th so that its mantissa is here and a whole bunch of zeros and then some ones, and its exponent is the same as the exponent for 7. So now I can add the mantissas, and what happens? Boom, nothing if you want, because 10 to the minus 7th is just too small a mantissa to have any effect. So when you write 7 plus 10 to the minus 7th on a computer, when you add them on a computer, you get 7 as an answer. And notice, you may think I was being lazy, because I'm not saying approximately here, I'm saying equal to. Well, I am lazy probably as well, but what this means is, on a computer, these are exactly equal. If you say, is 7 plus 10 to minus 7 equal to 7, the answer is yes. Because in single precision, you lose any of the precision smaller numbers. So two things have happened here. Number one, the last digit in the computation was lost. The digit we needed to see the effect, it was in the 7th decimal place, but we only store 6, 6.5 maybe, so we lost it. That's called truncation error. It leads to round-off error when numbers come up. Sometimes it's called round-off error imprecisely. But it means for you, remember that any number 10 to the minus 7th or smaller in relative precision is ignored. Okay, so that's serious problem. Okay. So what is this machine precision? Well, as I said, this machine precision is a measure of the precision of any computation you do. It's a measure of the best precision you can get from that operating system, that computer language. And it's very easy. It says, if I have a computer number and I just keep adding a small number to it and make the number smaller or bigger, make a number bigger until at some point it changes the number, that's the machine precision. If you want, you can say, here in equation 1, we need to find the largest possible value of epsilon sub m, epsilon meaning some relative error, m meaning machine, so this is machine precision, the largest value of this small number such that when we add it to 1 as stored on the computer gives us 1 back. So to repeat, you can always find a very small number, which is true. We want the largest of all the small numbers. Okay? And so this has an effect. It means anytime x being any number stored on the computer, the relative precision is at best 10 to the minus 7th for singles and 10 to the minus 16th approximately for doubles. You can worry exactly what it is, but speaking of errors, you don't have to worry about exact numbers, because if you knew exactly what it was, you wouldn't have any error. So as our model, and this is sort of, how scientists do things. We don't try to remember a whole bunch of things. You could say, and now we're becoming mathematicians if you want, applied mathematicians. Mathematician would say, aha, x sub c, the number we store as on the computer for x, is really the number x as a mathematician would know it, times 1 plus or minus epsilon, where epsilon is some small number and its magnitude is less than machine precision. So the number stored on the computer is x sub c, is equal to x with some relative error, which could be 0 error, or it could be a number as large as epsilon sub m. So, as we've said before, if you're a scientist, don't do your calculations single precision, because 6½ decimal places is hardly ever enough. Okay, so now, that sounded complicated. It's fun. This is not us making the rules. This is someone else making the rules the computer has to follow. So now let's go to the lab and see how we affect this in the laboratory. What happens in the lab. Okay, so now, let's get to work. Let's look and see the effect of machine precision on some actual calculations. So, let me tell you, you've done some lab work before. Now again, we're going to try to break the computer. We want you to experiment. We want you to see what doesn't work. You can't do any real harm. Your instructor can always help you if things go wrong, but you need to know what's going on, and you need to know what happens when things don't work right. So, I've been teaching for decades now, and a lot of the stuff I teach can be very high level, graduate, beyond, PhD level, theoretical particle physics. Some can be ordinary freshmen. It doesn't really matter. The game is very much the same whatever you're teaching, and most of it can be boiled down to 3 or 4 rules. The first rule of education, I may as well tell you now when you have to get to the lab and you have to face some of this, is most of education is just learning what the names mean. If we can tell you what the names mean and they make sense to you, the ideas are pretty simple. Even these highfalutin people, they have simple ideas. They just use these terms. You don't know what the terms mean. Once you know what the terms mean, the ideas are pretty simple. We throw a lot of terms at you. We throw a lot of concepts, and worse than that, in a course like this, we mix computer science together with math, neither of which is simple, and then we mix it together soon, I hope, with physics, which is not known for being easy for everyone, and you tend to get confused. Good. Confusion is the first step to understanding. It means that you're thinking about something, you're trying to develop a mental model in your head of how these things go together, and I'm trying to control you a little bit to help you develop that model as best you can, but it's up to you to develop the model. It's up to you to think about these things and have them make sense to you. If all you try to do is memorize what I say or someone else says, you're not really developing your mind the way you need to. You need to get confused, because only when you're confused can you figure your way out, and then you remember for next time. one of the best ways of figuring your way out is traumatic experiences. It must be a survival skill we inherited from dogs or something. You know, if it hurts, we remember that next time and we try not to do it. The stove is hot. Once you have to do it, but then you don't have to do it again. So when you go into labs and you get confused and you get frustrated because the computer's not working, sit back and say, that's not all bad. That's the purpose of this. Things are not always meant to be smooth. Computer things won't always be smooth. And even what we tell you may work now, it may not work in the future. So here's your first problem. Sit down at the computer, lab 1, and determine your machine precision. If you think you're smart enough, go ahead and don't listen to the rest of what I have to tell you here. Just go ahead and do it. But if you think you could use a little help this time in your life, we'll step you through it. So we want you to determine epsilon sub m, machine precision, for your computer. How would you do this? Remember, we define machine precision as a small number, the largest possible small number you can add to 1 as stored on the computer, and still have the computer think the number is 1. So here's a little code. And it's again a pseudocode, which means it's not any one computer language. And we again have a do loop, and then indented here is what gets repeated some large number of times. So we're starting with a value of epsilon of 1. We call it eps. 1's not a small number, so we're going to have to make it smaller. So each time we go through the loop, we divide eps by 2, we make it smaller by a factor of 2, we add it to 1, and then we print out 1 and epsilon. And you print it out, make sure it's printed out in enough precision so that you can see all the digits, and at some point this number will be less than 1. So here in the pseudocode, notice that we add the number 1, the actual number 1 point, to epsilon. And then we print out both the number 1 and epsilon. So at some point, when your computer is printing out to all the precision for a single or a double that you have, you'll see that the number the computer has stored as 1, this ONE 1, will actually be 1. And then at that point, you know that epsilon is machine precision, at least within a factor of 2, because that's all we're doing here, dividing by 2. Okay, so here we ask you to do it first for single precision. Then you should get a number about 10 to the minus 7th, but it shouldn't be, you know, what I say, it's whatever the computer says, and I say about, so you have to figure it out. Okay? And then repeat the whole calculation for double precision. So both singles and doubles are floating point numbers, but they should give you different answers. Floating point double precision should give you about 10 to the minus 16th. But you'll go see yourself. Now, as optional, do a better job. Determine what this machine precision is to as good a number as you can. How do you do that? Well, obviously that means if all we're doing here is dividing by 2, you can only get the answer within a factor of 2. See if you can do better than that. But don't be dumb, you know. You may have to run this a few thousand or hundreds of times, maybe a million times, to see just where it occurs. Once you know where it occurs, then you go back, and you don't start from 1 again. You start just in the range where you know overflow or underflow occurs, or where, in this case, 1 is just about equal to actual 1 point, and then you can zero in on the effect. Okay, so see how close you can get. Some students say, I really want to know what it is. Okay, well, it's fine with me to do this in decimal precision. As we've said before, computers don't store decimal numbers. If you really want to see what's going on, you need to speak the computer's language. So then you need to look at the binary, but binary is too hard and too long. So look at the octal or hexadecimal representations, and then you'll see exactly what the numbers are. Okay, so Lab 2 slide shows the next exercise, in this case looking at floating point numbers and their effect on calculations. We've seen this before, okay, and we'll see this again in various ways. This is now, the equation up here is, mathematically, it's just the Taylor series expansion for the exponential. Okay? And if you kept an infinite number of terms, you'd have the definition of an exponential. In this case, exponential of minus x. As an algorithm, we have, we'll just stop summing at a finite number of terms, capital N. That's the algorithm. And then what's left over, what we don't sum over, is called the remainder. Okay? And each term in this series, here written in sort of teletype font, which means it's supposed to look like an old-fashioned terminal. You've probably never seen one, but they used to print things out like this, so that's what we use to remind you it's computer talk. So this is a term in the series, and the whole sum will store as a variable. So the algorithm is written here to say the sum will store, that's the variable name, will be the sum of one, a term, another term, and so forth in the series. I want you to do this calculation as your exercise for large and small values of x. I should really say small and large values, because if you start with a small value of x, like 0.1, then this series should converge very well, because if you raise 0.1 to a high power, you get next to nothing. So the series converges, these terms fall away, and you know the remainder will be very small. If you use a very large value for x, and you raise x to a very large number, like 1,000, you get a very large number in the numerator here, and then n factorial, 1,000, is another very large number. At some point, the factorial always wins over the exponent, and the terms begin to get smaller. So mathematically, the series always converges. But on a computer, there's no guarantee you can ever get that far before what happens? Overflow. Okay? So this is a problem. If you go too far, the numerator and the denominator can both overflow, the computer will stop, you get garbage. Likewise, if you go too far, you add so many terms together that you get round-off error coming in, truncation error, because these terms at some point have to cancel each other out in order for the series to start getting smaller again. The terms get smaller, at least when x is greater than 1. Because when x is greater than 1, the numerators are always increasing, so the terms increase. At some point that has to decrease. So, okay. As if life isn't hard enough, now we're saying, you just can't sum to get a value for this. I want you to do better than slide rule accuracy. I want you to have this calculation done with one place in the eighth being the error. Okay? So we want 8 places of precision, be off maybe by 1 decimal point in the 8th place. Okay? So we say we want 1 part in 10 to the 8th. How do you do that? Well, that's hard unless you know the right answer, but you're not supposed to know the right answer. So we'll assume here to say, okay, we really want the remainder to be relative to this to be 1 part in 10 to the 8th. But we can say, if the last term we include divided by the sum, in other words, all the terms we've included, one term divided by the sum is less than 10 to the minus 8th, then it's a good bet, not an absolute positive bet, but a good bet that the remainder is less than 10 to the minus 8th relatively, and then that's the precision we want. Okay? So the assumption then is that the remainder term is small and there's no round-off error. But that's the algorithm. So go ahead, try this on the computer. I'm being too nice to you. So let's look at slide 3 here. So slide 3, and you can ignore this if you want, if you don't like people being too nice to you. But here I tell you how to do it. Okay? So we have on top the algorithm we're using, just a finite number of terms. And we have in green here, we have another pseudocode, and it looks just the same as the other pseudocode. There's a bunch of initialization. We start off, we said term, that's each term in the sum. Sum here 1, epsilon 10 to the minus 8th, okay? So that's sort of the relative precision variable, obviously. Then we have a do loop. The do loop means we repeat this n times, normally. But this is a different kind of do loop, and here we're repeating this, a while loop if you want. We're repeating this while the condition that the term in the sum divided by the sum, absolute value, is greater than epsilon. So this is a loop which keeps repeating an indefinite number of times as long as the error is greater than epsilon. And certainly my advisor would tell me, Rubin, You don't do while loops on a computer, because if you make a mistake or if the series doesn't converge, it goes on forever and somebody else is paying the bills for you, and that could be very expensive. Now hardly anyone pays computers by the hour, by the minute, or by the second, so it doesn't matter. But there is a warning here, especially as you get to write bigger codes. While loops don't have to end, in which case if your program seems to be running forever, you made a mistake, which happens, you may want to quit. Okay. Now, let's look at this series up above, the mathematical equation, and let's look at the code. As we've mentioned in the book, for sure, the best way to compute this is not to compute n factorial, because n factorial is very, very large. It may overflow, and x to the n may overflow. But if you look at how one term is related to the other, the preceding term, in the series, each term just increases by a single power of x divided by wherever you are, n, small n if you want the index of the code. So if we just say, we do this for I being a counting, a number, an integer, and we just change the new term is equal to the old term by times minus 1 times x over I, we never have to calculate factorials. So this is what I call the good way, good in quotes. This is a good way to do the sum. We never have to worry about overflows. The bad way would be if you do the factorial down below, and in the exponent x to the n, we'd have overflow problems. And I can guarantee you, try both. First try it the bad way, see how good your answers are, and see overflows come in. Then try it the good way, which eliminates overflows. Okay. What do you look at? Well, since this is early in the course and you haven't done too many of these things in the lab before, let me give you a hint. You don't want to look at a screen of numbers, and you don't want to just print out a screen of numbers, but you want to print out, at least for the parts of the calculation where the action's occurring, we want a nice table. You can align them. In Fortran, that's very easy. C, that's easy. In Java, now if you use the Java's formatted output, you can align things nicely. If not, try as best you can. What we want is a table with columns. Columns go up and down. Okay. First column will be the value of x, and remember, it starts small, then large. How many terms, capital N, you've used in the sum, the actual value of the sum, and then the sum that you've calculated as your algorithm minus the exact value, e minus x, and the whole thing divided by the sum. So this would be, the last term here will be your relative error in the calculation. You may ask, how do I know the exact value? Well, you could assume that the people who wrote the compilers and the mathematical subroutine library are worth their weight, at least for this simple a calculation. So you can use the built-in values for exponential. So in Java, that's math.exp. It's in the math library. Fortran C, it's in the mathematics library as well. You have to include those. Okay. And compare, when you're done, two tables like this, both the good method and the bad method. Again, the good method won't have overflow problems, but it will have round-off error. So that's all you have to do for this exercise, and then you'll have both a feel for when floating point overflow occurs, maybe underflows, some of these terms may get very small, and certainly how round-off error comes about. Because what you should see is as x gets larger, the series may converge, but it may not give you a good answer. And when x is really large, it may not converge at all. So try to notice those differences and see what your computer does. Next time we'll talk about some new subjects, but don't go ahead and do that. Make sure you understand this stuff before we get ahead. See you soon. Bye-bye.